One example of having the derivative as rate of change is applying it on one-dimensional motion, or what is known as rectilinear motion. So, to start off, we first define the position function. So, if we have a particle or an object in rectilinear motion or in one-dimensional motion that moves along an s-axis so that its position coordinate function of time t is s is equal to f of t, then the function f is called the position function of the particle. So, say for example, we would have this s-axis. We have this s-axis. We have this one here. And then, from here, let's say this is your initial position, x sub 1, and then you have, this is x sub 2, x sub 3, and so on. So if your particle is from here, once it moves from here, then goes back, or goes further, then stops here, then if this is described by s is equal to f of t, where the independent variable is time, then this is what we call it. The t looks like f of t. Then this is what we call our position function. So the position function technically tells us where the particle or the object is given a specific time interval. There. So from there, since we have a specific position for a certain specific time, we now define displacement. So we define displacement here. If t sub 0 to t sub 0 plus h is a given time interval, then the displacement of a particle over this time interval is defined to be the difference between the particle's initial and final position coordinates. So the displacement over this time interval is f of t sub 0 plus h minus f of t sub 0. This is also actually the definition of displacement in physics. It's not just more, it's just a bit more simplified, probably when you encountered physics during high school. But it's the same definition of displacement, not distance, but displacement. So with that, since we have already defined displacement, one of the things that we usually account for is how fast an object or a particle moves. And what we've learned before in your secondary education or in high school would be the average velocity. So suppose that a particle in rectilinear motion along an s-axis has a position function s is equal to f of t. Then the average velocity v sub average of the particle over this time interval, given that h is positive, is defined to be this difference quotient, the displacement over the change in time. This h came from the fact that since this is from t sub 0 plus h minus t sub 0, this is the difference quotient that we have seen in many examples before in our class. So t sub 0 plus h minus t sub 0, this gets cancelled, hence the h. So that is average velocity. However, since we already know how to get the derivative, which is the rate of change at a certain point, we don't just get the average, because the average would be, for example, we have our s-axis, we have our s-axis here, and say this is your particle. This is where your particle is at t sub 0. At t sub 0. So once it moves to t sub 0 plus h, let's say the particle is already here. So the average distance it moved from here to here, the average velocity or the average speed, how fast the particle moved over this time interval, that's what we get. We do not get the specific speed or velocity of the object at a specific point. Say here, we don't know what is the velocity of the object at that specific point. We only get the average velocity of the average velocity between these two positions. So there. Remember, we are not, although I've been interchanging velocity and speed, remember that speed is, doesn't have direction, but velocity has direction. But they both tell how fast an object moves. But then again, this is average. Since we know the derivative, we can then know in particular what's the instantaneous velocity of an object at a specific point. So the instantaneous velocity is defined to be, given the position function s is equal to f of t, the instantaneous velocity of the particle defined at t units of time is v units of velocity, where velocity is equal to the first derivative of the position function, if it exists. So remember, there are derivatives that do not exist. Do take note that the positive velocity means we move at a positive direction, and the negative velocity means we move at a negative direction. Also, we don't just care about velocity, how fast an object moves, we also care about how fast that object moves fast, and that is acceleration. So how fast an object moves, that's your velocity with direction. How fast the object moves fast, or how fast that does it change its position over time, that's acceleration. So given the position function, the instantaneous acceleration is actually the derivative of the velocity function, which goes to say that the acceleration function, let's say the acceleration function is actually the second derivative of the position function. The velocity function is equal to the first derivative of the position function. That's why in our previous lesson of higher order derivatives, there was already a mention of velocity and acceleration. So velocity is the first derivative of position, acceleration is the second derivative of position, and also the first derivative of the velocity. Because as we define, acceleration is the rate of change of the velocity, while velocity is the rate of change of the position. Hence the use of derivative. So now let's have some problems involving rectilinear motion. So we have number 1 here. We have a particle moving along a horizontal line. A particle is moving, along the horizontal line according to the equation s is equal to t cubed minus 12t squared plus 36t minus 24, given that t is greater than or equal to 0, since we're considering t is time. What are the intervals in which the particle is moving to the right, moving to the left, and then at rest? Since we're given with the position, and we need the intervals where it's moving, we have to check its velocity, because velocity is the one that tells us the direction of where it is moving. And since we're moving to the right and left, right is positive, left is negative in the horizontal line. So first we get the first derivative of this. So ds over dt would be equal to 3t squared minus 24t plus 36. That's the first derivative of our position function. Now, to get intervals, to divide the horizontal line to intervals, what we can do is equate this to 0. So that the factors, or the roots rather, of our equation can serve as the ones that would divide our horizontal number line. So again, may I repeat that? We can now equate this to 0 to get roots that would divide the horizontal number line. So we equate now 3t squared minus 24t plus 36 equals 0. So now we solve that equation. And as we can see, this is actually divisible by 3. So we divide both sides of the equation by 3. And then we get t squared minus 8t plus 12 equals 0. Then factoring this out, we have t minus 2 times t minus 6 equals 0. Therefore, the roots of this is actually the velocity function already, would be t is equal to 2 and t is equal to 6. I would just have to show first that I have t minus 2 equals 0 and t minus 6 equals 0. So t is equal to 2 and t is equal to 6. So hence, if we have our number line here, so we would have, not the number line, there. So if we now have our intervals, time intervals, we would have less than 2 seconds, wrong symbol, less than 2 seconds equal to 2 seconds, no, it just says this particular time interval, so let's just stick with that. Then t is in between 2 and 6, t is equal to 6, then t is greater than 6. So using 2 and 6, the roots that we got as our endpoints of intervals, it will be easier for us to analyze. Now, how do we know whether it's moving to the right or to the left? Remember, a while ago we mentioned position. The positive velocity is positive, negative velocity is negative direction. So that would mean that we moving to the right, we should have a positive velocity, and moving to the left, we have negative velocity. That's positive velocity, negative velocity, and at rest, it's not moving. So velocity would be equal to 0. So now, how do we check whether we have positive or negative velocity or it's equal to 0? We now substitute any number within the interval in our velocity function, which is our ds over dt. For example, in time interval t is less than 2, let's say 1, what would be 3 times 1 squared minus 24 times 1 plus 36? What would the answer to that, and what would be the sign of that answer? So, that would now, by the way, this has to be greater than 0 because of this. Sorry about that. So now we're going to have, we don't actually care about the answer, but we care about the value. But the answer to this would be positive 15. So it's positive. So since the answer is positive, our direction, you can say that it moves to the right. At t equals 2, we're going to have 3 times 2 squared minus 24 times 2 plus 36. But if you're going to look at it carefully, we were actually able to solve that t, not there, here. T is equal to 2 and t equal to 6 is when the velocity function is equal to 0. So already here, we can say that this is 0, and even here, here, 3 times 6 squared minus 24 times 6 plus 36, that will be equal to 0. So at these two exact time intervals, the particle is at rest. So we already have an answer for letter C. So now here, somewhat in between, we can choose any number, say 3. So it's the smallest. 3 times, it's the smallest integer. So 3 times 3 squared minus 24 times 3 plus 36, and that gives us negative 9. So this is negative, so it goes to the left. So now for greater than 6, the smallest integer is 7. It's good for us to compute. Therefore, this becomes positive 15. So this becomes positive 15, so it moves to the right. So just to summarize and to answer it as A, B, C, at what are the intervals in which the particle moves to the right? That would be the intervals from t is greater than 0 and greater than 2. time units and t is greater than 6. It moves only to the left during the time interval t is between 2 to 6. And it will be at rest at t is equal to 2 and t is equal to 6. So the time interval equals 2, the particle stops. It doesn't move. The particle equals 6. At time interval equals 6. It will also stop. So that's our answer for number 1. Now let's have number 2. At t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. The position function of the diver is given by s of t is equal to negative 16t squared plus 16t plus 32, where s is measured in feet and t is measured in seconds. When we're asked when does the diver hit the water and what's the diver's velocity at impact. So the question is, when does the diver hit the water? So let's just have that. So for number 2, we would have again our position function. S of t is equal to negative 16t squared plus 16t plus 32. Oops, fix that. Alright, so we are asked when does the diver hit the water. So if we're going to imagine this is the platform and then this is the diver, once it goes down, so the position of that going down, so if that's the water, then this would be 0. Because it's above water level, that would be positive. Because it's below water level, then that would be negative. So the water itself would be 0. That means we have to solve when, that's the time, we have to solve for t, when s of t, what would be t when s of t equals 0. Therefore, we have to solve negative 16t squared plus 16t plus 32 equals 0. I'm going to divide everything by negative 16. So it's easier to solve. We have a t squared positive. We're going to have t squared minus t minus 2 equals 0. So solving this, factoring this, I'm going to have t equals t minus 2 times t plus 1 equals 0. So for t, have t equals negative 1 and 2. But since negative 1 cannot be time because that is negative, this becomes an extraneous solution. Therefore, the only valid time is that the diver will hit the water at t is equal to 2. Let's just confirm the time unit. Seconds. 2 seconds. Therefore, the diver will hit, when it's a diver will hit the water at 2 seconds. There you go. Now, sorry, this is A. So for B, what will now be the diver's velocity after impact? So again, we are told that the velocity function given time would be the first derivative of the position function. Therefore, we need to find the first derivative of our s of t, and that is equal to negative 32t plus 60. So, since we are told that at impact, that's t equals 2 seconds, the velocity at 2 seconds will be negative 32 times 2 plus 16. That would give us now an answer of negative 48. Therefore, the velocity of the diver at 2 seconds is negative 48 feet per second. It's negative because he's falling down. He or she is falling down. For number 3, we are given the problem. A particle is moving along a line according to the equation of motion. S is equal to 1/2 t squared plus 4t over t plus 1. where s meters is the directed distance of the particle from the origin at t seconds. If v meters per second is the instantaneous velocity and a meter per second squared is the instantaneous acceleration at t seconds, we're asked to solve for the values of t, s, and v where a is equal to 0. Since we're given where a is equal to 0 and we know that a is actually the second derivative of our position function, that will actually look like d over dt of ds over dt. Sorry. It looks like d squared s over dt squared, second derivative. So we have to find the second derivative of this. So first, for the first derivative, s ds over dt, ds over dt that would be equal to, this simply becomes t, but the second term is a bit more complicated, so we'll use quotient rule here. So we have low derivative I minus I, that's the derivative of low all over low squared by quotient rule. So therefore, I'm going to just have t plus, this becomes 4t plus 4 minus 4t over t plus 1 squared. It's cancelled, therefore, ds over dt, which is actually equal to our velocity function, is t plus 4 over t plus 1 squared. Now, second derivative, which is our acceleration, is d squared s over dt squared, that will now be equal to the derivative of this one. So therefore, derivative of t is simply 1. Then we, here, although we can use quotient rule, it might, since it's the one on top is a constant, maybe we can just change it so that it will not be as tedious. We just need to use a little bit of power rule. Because this one here can be written as 4 times t plus 1 raised to negative 2. Therefore, I'm going to have plus 4 times the derivative of this is negative 2 times t plus 1 raised to negative 2 minus 1. That would be 1 plus 4 times negative 2 times t plus 1 raised to negative 3. This will then become 1 plus 4 times negative 2 over t plus 1 cubed, but that's in the denominator. Hence, the second derivative of the position function becomes 1 minus 8 over t plus 1 cubed. This is where we actually start because we are told a is equal to 0. So we would equate this to 0. That's 1 minus 8 over, if we change it to here, so we're going to have, we're going to have 1 minus 8 over t, t plus 1 cubed is equal to 0. Then we have to solve for t. So we transpose it, I'm going to have 1 is equal to 8 over t plus 1 cubed. By cross multiplication, I'm going to have t plus 1 cubed is equal to 8. Getting the cube root of each side, because that's cube, so we get the cube root, we're going to get t plus 1 is equal to 2. And we don't need plus minus because it's an odd root. So it will just really be 2. Transposing, that's 2, t becomes 2 minus 1. Therefore, t is equal to 1 second. So at 1 second, our acceleration is actually equal to 0. And that's actually one of the things that we're looking for, the value of t when t equals 0. So now that we have t, we just need to look for v and s. So we'll look for v first, then s, because that's the last going backwards. So now solving for v, which is actually ds over dt, at 1 second, v of 1 will then be equal now to, that would then be, that's 1 plus 4 over t equals 1, 1 plus 1 squared. Therefore, solving for this, we're going to get 1 plus 4 over 2 squared, which is 1 over 4 over 4, that's 1 over 1, which is equal to 2. So, at 1 second, where the acceleration is 0, the velocity, here, the velocity at 1 second, would be 2 meters per second. So, at 1 second, where a is 0, the velocity at 1 second is 2 meters per second. And to find where the particle is at this specific situation, we now solve for s of 1. That will be 1 half times 1 squared plus 4 times 1 over 1 plus 1. I'm going to have 1 half plus 4 over 2. Therefore, I'm going to have 5 halves. So, 5 halves meters. Therefore, when the acceleration is equal to 0, that's t is equal to exactly 1 second. The object is going at 2 meters per second, and the object is already at the position of 5 halves meters from the origin. Oops, sorry. There you go. So let's have more examples of rectilinear motion. So we have here, in physics, free-falling objects use the position function. S of t is equal to negative 16t squared plus v sub o t plus s sub o, where s feet is the height of the object at t seconds. S sub o is the initial height of the object, and v sub o feet per second is the object's initial velocity. A silver dollar is dropped from the building that is 1,296 feet tall. We are asked to determine the position and velocity function for the coin, the instantaneous velocity at t equals 1 and t equals 2, and the velocity of the coin at the impact. So first, we're given with the template of the function. It's negative 16 squared plus v sub o t plus s sub o. Now, we are told that a silver dollar is dropped from a building that is 1,296 feet tall. So that would be your initial height, 1,296 feet. However, since it's just being dropped, the initial velocity is actually 0 meters per second because you're holding it, it's not moving at 1,296 because it's just being dropped. So, 0. Therefore, for A, the position function of the situation will be negative 16t squared, this is 0, it will be to the right, plus 1,296. And now to look for our velocity function, we just need to find the derivative of the position function. And that will now give us negative 32t, derivative of the constant t. So that's your answer in letter A. So now in letter B, we're asked to determine the instantaneous velocity at t equals 1 and t equals 2. So the instantaneous velocity is v of 1 and v of 2. So for v of 1 first, we're simply going to have negative 32 times 1. So we are going to have negative 32 meters per second. However, at v of 2, it will be negative 32 times 2 will be negative 64 meters per second. So it's going faster as it's being dropped. At 1 second, it's just going down at negative 32 meters per second. But at 2 seconds, it's already going down at negative 64 meters per second. There. Now in letter C, find the velocity of the coin at impact. So at impact, we first need to find the time that we need to have as input in our velocity function. So first, we'll put C here. Impact, at impact, that's S of t is equal to 0. Impact on the ground. That means we have to solve negative 16t squared plus 1296 equals 0. We'll just transpose because there's no other variable. Negative 16t squared is equal to negative 1296. Divide both sides by negative 16. T squared would be equal to 81. Getting the square root here, t would be equal to positive or negative 9. We don't have a negative seconds, so therefore t is equal to 9 seconds. Which would mean that after 9 seconds, the coin is already at the ground. What would then be the velocity of the coin at that impact? So that would be v of 9. It's negative 32 times 9, which would already be negative, if I'm not mistaken, 288 meters per second. There. So the answer for this is this one. Negative 288 meters per second. Now let's go to number 2. A stone is dropped from a height of 256 feet. Use the equation of motion for free fall, which is actually what we had in number 1. To write the equation of motion of the stone, find the velocity of the stone at 1 and 2 seconds, and when does it reach the ground and how fast it is going when it reaches the ground. So, since it's dropped again, since it's dropped again for number 2, the equation of motion for free fall would be negative 16 squared plus v sub o t plus s sub o. Since we are asked for a and b, equation of motion of the stone. Our initial height is 256 feet, but since it's being dropped, it doesn't have any initial velocity to be 0. So once again, our position function is negative 16t squared plus 256. This is one equation of motion of the stone, although it just talks about position. So for the velocity function, we find its first derivative, which is equal to negative 32t. So there, we have two equations of motion already, our position and our velocity. If you want to find acceleration, it's also an equation of motion, although the acceleration of the falling object becomes constant at negative 32 feet per second, which is actually the estimated or the approximate acceleration due to gravity in feet per second. So that's A. In B, we're asked to find the velocity of the stone at 1 and 2 seconds. So just like what we had a while ago, v sub 1, that would be negative 32 times 1, and that would be negative 32 meters per second. And the second one is negative 32 times 2, so we have negative 64 meters per second. So there you go. In C, when does it reach the ground? So therefore, we are asked when is S of t equal to 0. So solving, that's negative 16t squared plus 256 equals 0. So if we're going to solve that, that's negative 256. Divide both sides by negative 16. T squared would be equal to 16. So getting the square root, t would be equal to plus minus 4. But since we don't have negative time, t is equal to 4 seconds. And finally, in letter D, how fast is it going when it reaches the ground? That's the velocity at 4 seconds. So therefore, we're going to simply have negative 32 times 4, which gives us negative 128 meters per second. That's your answer in number 2. Alright, let's figure that out for our last problem in number 3. we have a ball is given a push so that it has an initial velocity v sub 0 of 24 feet per second down an inclined plane. Then, S, the position function is 24t plus 10t squared, where s feet is the distance of the ball from the starting point at t seconds. And the positive direction is going down the inclined plane. So the positive, if this is your inclined plane, this is positive, that is negative. We are now asked, how long does it take for the velocity to increase to 48 feet per second? So since we're asked for velocity, we need the velocity function. V, which is equal to ds over dt, is equal to, that's 24 plus 20t, getting the derivative of our position function. How long does it take for this to be equal to 48? Hence, that's 24 plus 20t equals 48. Then we solve for t because that's how long. So transpose, we're going to get 20t is equal to 48 minus 24. Then we're going to get 20t is equal to 24. Divide both sides by 20. So at time t is equal to around 6/5 second. 6/5, there you go. 6/5 or 6/5 second. That's the time that exact second is when the velocity of the ball becomes 48 meters per second. And those are examples of rectilinear motion.